Unfortunately, I already have the award, so I don't have to. Should I use the mic?
Yeah.
No. Okay. So me and Andre Kish, we wrote this paper, Promising Approach to Debugging Remote Promises, on my way to my master's thesis. And I'm going to talk about the idea in the paper, and I'll also tell you at the end kind of what we got out of it in the end, because the idea changed over time. So a short disclaimer at the beginning, because in previous presentations people have been sort of picky about what my understanding of promise is. I'm not going to enter any discussion about, well, what's the difference between futures and promises and all that kind of stuff. This is really just a prototype implementation, and the thing that's interesting is the idea, the core idea behind promises. And yeah. So what is the motivation behind the paper? So imagine that you have a local computer, and then you have some remote machine, and what you want to do is, for instance, request a file list. This is just some dumb example. Just imagine anything that you want to get, which may take a while. So in the naive case, you make the request, and then you just block and wait until you get the result. And well, yeah. But what would actually be nice is something like this, right? You want to fire off the request and use the time you would be blocking otherwise to do more work. You want to reduce the time that you're waiting for anything as much as possible. So with promises, this is quite easy. So I'm quickly going to introduce the concept just so you know what I'm talking about. A promise is basically an object that synchronizes concurrent threads, if you will. And what you do is you ask the promise to perform the operation, and the promise will synchronize the remote operation with the local one. So in this case, when you have a promise, you can do work locally as well as remotely, just as I showed before. And what's nice about promises is that at some point locally you will want to use this value that is going to be returned. So you want to use the file list, right? But what you don't know is if the value is there yet. And you also don't want to have to manually check that, because, well, what do you do? Enter some kind of polling loop or something. You don't want to care about that. So the promise takes care of that for you. So if you ask the promise for the value and the value is not yet there, it will block until the value becomes available, and then you can proceed. So you don't have to do the synchronization yourself. So promises are also known as futures in Java, and tasks, for instance, in Visual Studio, like C#. So how does this look in code? This is the implementation that I wrote. This is not the perfect implementation, but it's one way to express what I'm talking about. You specify the operation you want to do. You can do that inside a block, so that you can defer the operation, and then you say promise. And the temporary variable here will hold a promise object, right? And then at some point, after you've done some work, you just ask this promise object for the value. That's basically the entire magic. So if you have that, the problem becomes, or there's one problem, and that is if there's an error during execution of the promise on the remote host, what do you do? And how do you know what happened? How do you recover? There are obviously different ways to handle this. One is to return null, which probably is not a good idea. Well, maybe you could return a description that says, hey, you know, this went wrong, but still the thing has aborted and you'll have to, yeah, you still can't proceed from there. So maybe there's a better way. Stack trace, so you can at least look at what the objects were holding. But actually, what I'd like is some kind of exception object, right? And ideally, I would like a debugger. So if I have a debugger, as we know it from Smalltalk, oh cool, I can restart stuff, I can resume. And this is then remotely, actually. So how do you do this? Just to refresh your understanding of how processes work in Smalltalk, you have a context object which represents an activation record. The context forms a list, so the contexts form a list, which is the stack, like in C, where you have just a list of functions that call each other. It's the same concept. And you have the process that points to this list of contexts. The process is basically a wrapper object. The context knows the compiled method. It is an activation record, and the compiled method it references is the method that is being activated. And then there's the receiver. So this is the graphical representation of what I just showed you, and the nil at the bottom is just like the last activation record, so you know where the process ends. Okay, so now imagine you have two of these, right? In the example I'm talking about, process 1 in this case would be on a local machine, and process 2 would be on a remote machine. And now this is pretty trivial actually. In a usual case you would have two debuggers, right? If you have, if you debug the local process, you have a local debugger. If you debug the remote process, you have a debugger in the remote image, or ideally you have a remote debugger, but still you have two debuggers. But if you do this, create one virtual process, then you only need one debugger. You get everything for free. So what we do is we create a virtual process out of arbitrarily many Smalltalk processes, and I'm going to show you how that looks quickly. So for reasons, I cannot run Pharo on my MacBook because I'm using the macOS beta and the VM doesn't work. So I'm going to have to do this in Ubuntu. Okay, so this image already contains the code that I use, and what I'm going to do is I'm just going to create a new class and create a new package quickly. And I'm going to call this file list getter. Oh, wrong combination. And I'm going to create a single method on the class side, which will open the transcript and output hello. The reason I'm doing that is that you can see that I'm not cheating and that there's actually something going on in the remote image. And then I'm going to send another message, and this message will not be implemented, so there will be an error. copy of this image, and then I'm going to start the copy. No, that was the wrong image, sorry. Okay. So now I have a remote communication framework that I use, which I'm going to talk about later. So I have to start the server over here, which is now running, and now in my local image I'm going to make the request for the file list, right? So what I do here is I create the address on which the server is running with the remote server. Then I execute the code that I want, and I have this remote promise on. This is a wrapper that takes care of initializing the communication, but apart from that it's just a regular promise. Right, so what I do here is I tell my promise to open a debugger when there's an exception, because it has to be configurable what you want to do depending on whether you're in a production environment or not. And so what I do internally is I store, I have state that tells me if there was an exception, and I have references to the exception and so on. And then I have to tell it to run. Okay, so let's do this. So it's running now. You see here the transcript triggered in the remote image. So now I'm doing I can still do work here, right? You've noticed no debugger was opened yet because I didn't request a value. So if I request a value, then I get my promise debugger. And you'll notice that this is not particularly beautiful, but that is not the point. The point is that, oh yeah, that was some weird error I got yesterday. I'll try that again. Okay. Sorry, this is obviously the demo effect. Yeah, that's better. Okay. So what you see is this is a bit slower because it communicates via the network. You see on the left we have seamless proxy. You might have seen that in Dennis's presentation about the remote debugger. That's because I use his framework. The error is what we expected it to be, namely that the message has not been implemented yet. And as you see, I can look at the method, which is actually a proxy, right? This is not the method that I have locally. And now the interesting thing is, if you look at this is the doit that I executed remotely. And if I scroll down, there's another doit, which is the local process's doit, right? And I can go down the stack here, and you'll notice on the left the names of the classes are now no proxies. These are objects that I have locally, and I can go down until I end up at new process. So these are really two processes, one local and one remote. Okay, I'll rush through the rest. So there are obviously some concerns about the internals of this. I've done some testing on memory and performance, and I just want to quickly go through them. So this is not very interesting, but just to show you what we have to keep in mind is how the virtual machine, the current virtual machine in this case, stores objects. So So this is an object header. The object format looks like this. There's an object header, so every object has this, and then there's an optional extended header, and below that there's the number of slots, right? So the number of instance variables. And for contexts, this is also true. You have the object header, and then you have a number of instance variables, and you have either 16 or 56 variable slots. The variable slots represent a stack machine, so it's not really important what this does. It's just you need to understand that there are two kinds of contexts. So contexts come in exactly two sizes. And the reason for this is an optimization. You could have variably sized contexts, but for performance reasons in the virtual machine they use two sizes. And there's no extended header here. So what this means is you get contexts of size either 96 bytes or 256 bytes per instance. And the reason I'm showing you this is that in order to put these stacks on top of each other, I have to create a reference to the original process. And because I don't know in which state this process will be in, I create a copy. Okay. So that means I have to copy every context of the original process. And therefore I need to know how big contexts are. So interestingly, the number of contexts in a call stack are usually well below 1,000. So I made tests with 100,000 contexts. And so for 1,000 contexts, we end up with memory requirements of 512 kilobytes or 192 kilobytes. I have to multiply by 2 here because the virtual machine does not use real contexts all the time. But when you copy them, you have to create new instances. So actually you sometimes create 2 instances. But that's not really important. The important thing is that memory consumption for these extra contexts is actually not relevant in this when you put it in perspective to the rest of the memory that you use for large context programs. There's another problem that is a lot more difficult, and that is garbage collection. So this is a simplified view of an object graph. So every context references some objects like any other object. And now if you run the garbage collector on a context that is no longer needed because the process has returned from it, then the garbage collector will collect some of the graph. There may be other references to these objects. This is not a complete graph, just an example. So at least partially this graph has been collected, right? But what happens if you create a copy like I do? Okay, so now we have 2 references to the entire object graph. Okay, so now run the garbage collector, and oops, okay, so this has not been collected at all. So that means that because I create copies, I prevent the garbage collector from doing its job because I need all the objects that are still there. And oops. This is a problem that needs further investigation because it was just too much work to get good numbers. One would probably have to modify the garbage collector to get statistical information on real-world programs to make any statement about how bad this problem is. And the last point is performance. I was actually very surprised to find that when you create a promise and have to copy the process and have to reify the contexts, that nothing changes. right? So, yeah. So that's good, and I can't go through seamless, and yeah, okay. I want to tell you about threads, so this can be all implemented with threads. Thank you.
So, we don't have time for question except if it is very short. Okay. If they have questions, they can find suppose. Now we exchange the two last